Magandang araw! I hope everyone who is watching this video is safe, healthy, and happy. Now we will have a presentation on the rules of inference. This presentation would allow us to determine how logical outcomes are deduced, describe the rules of inference, and would allow us to identify appropriate rules of inference as justifications for formal proof. Now, suppose we have these propositions. No? I listen, which we denote by P, and then the proposition I understand the lesson by Q. Okay? So we could form the conditional form of these two propositions by saying, if I listen, then I understand the lesson, and denote it by P implies Q. Now, suppose we have the conditional, if I listen, then I understand the lesson. And then, P exists, such as we have I listen. We know earlier that P implies Q, and therefore, if we have the proposition I listen, which is P, therefore, the proposition I understand the lesson must exist. Okay, so we are able to infer the existence of Q from the propositions above. Then, if we have the same conditional, if I listen, then I understand the lesson. So P implies Q. But we have not Q, meaning it is not true that Q exists. Meaning, it is not true that I understand the lesson, such that I don't understand the lesson, not Q exists. Okay? So, not Q implies not P. And therefore, if not Q is present, it is logical to infer that not P also exists. Such that if we have P implies Q, and we have not Q, therefore we have not P. Okay, now we can try to describe the process that we had earlier and name them as rules, no? Rules of inference, so to speak. Now, the rules of inference is a set of rules, no, which would allow us to deduce conclusion from given propositions. Okay? So the first one that we had earlier is called Modus Ponens, such that if we have P implies Q, you have P implies Q, and then we have P, therefore Q exists. We can infer the existence of Q if we have the conditional P implies Q and another proposition P exists, therefore it follows that Q exists. We call that modus ponens. And then the next one that we had earlier is actually modus tollens, such that if we have the conditional P implies Q and we have not Q as the second premise, therefore we can infer that not P exists. Okay? And then we have the third rule, which is called hypothetical syllogism, where we have the conditional P implies Q and then Q implies R, and therefore we can infer that P implies R. So this is like the transitive property of real in real numbers, no? So it also exists in logic. Again, if P implies Q and Q implies R, therefore it is inferred that P implies R. The fourth rule is called disjunctive syllogism, where we have the disjunction P or Q, and then we have not P, therefore Q exists, no? So remember the rule for disjunction, no? If one of the disjuncts is true, the disjunction is true. We have P or Q, and it is not true that P exists. Therefore, it follows that Q must be true. Therefore, we can infer that Q exists. Okay, again, disjunctive syllogism, P or Q, we have not P, therefore Q. The fifth one, we have constructive dilemma. So we have a conjunction of two conditionals. So we have P implies Q and R implies S. if we have the second proposition P or Q, therefore we can infer the existence of Q or R. Notice that Q and S rather. So let me repeat that. If you have P implies Q and R implies S, we have another proposition P or R. Therefore, we can infer Q or S. Note that Q and S are the consequent of the two conditionals, and P and R are the antecedent. So that's the constructive dilemma. We have the destructive dilemma, again the existence of the conjunction of the two conditionals P implies Q and R implies S. This time we have not Q or not S, therefore we can infer not P or not R. So note that this time there is the existence of not Q or not S. Again, Q and S are the consequent of the two conditionals, and therefore we can infer the existence of not P or not R. The seventh rule is simplification, such that if we have the conjunction P and Q, therefore P exists. Okay? And then conjunction, if you have two propositions P, Q, therefore we can infer P and Q. Okay? So simplification is when we can infer the existence of the first conjunct P, whenever P and Q exist. And in conjunction, there must be the existence of two propositions PQ, and then we can infer the existence of the conjunction P and Q. The ninth rule is addition, such that if we have the proposition P, we can infer the existence of P or any proposition, say Q. Again, if P exists, we can infer P or Q. Q could be anything. And then the last one is absorption, such that if we have the conditional P implies Q, we can infer the existence of P implies P and Q. So those are the 10 rules of inference, and we try to identify the rules in the following examples. So we are asked to state the rule of inference by which the conclusion follows from its premise or premises. So we have the conjunction of two conditionals. For example, we have here A implies not B and not C implies D. And therefore, we have A implies not B. Note that this example takes the form P and Q, where our P is A implies not B, this whole thing is our P, and this whole thing, not C implies D, is our Q. And therefore, notice that we have this A implies not B, which is our P. So P and Q, and therefore we have P, that is simplification. Next, we have E implies not F, and therefore we have E implies not F or not G implies H. This example takes the pattern P, where P is E implies not F, and then we have P or this expression that G implies H takes Q. No, this should be Q. This should be Q. So we have P or Q, which is actually addition. So again, this should be Q. And then for the third example, we have O implies not P implies Q, and therefore we have O implies not P and not P implies Q. So note that this example takes the form P, where this thing is our P, and Q, where Q is not P implies Q. And therefore, we have the form P and Q. So this is our P and this is our Q. Clearly, this is an example of a conjunction. Next, we have not R if and only if S or T or U, and then we have not R if and only if S, and therefore we have T or U. Note that this example takes the form P or Q, and we have not P, so this not R if and only if S is our P, and if we negate that, we have not P. So we have the form P or Q, you have not P, and therefore Q, where Q is T or U, is an example of a disjunctive syllogism. Number 5, we have N implies O if and only if not P. We have O if and only if not P implies Q, and therefore we have N implies Q. When we observe the expression, we can see the pattern P implies Q, where our P is N and Q is O if and only if not P, such that we have P implies Q, Q implies R, and therefore we have P implies R. So we have P implies Q, Q implies R, and therefore we have P implies R, which is clearly an example of a hypothetical syllogism. And we have this example, E implies M, and therefore E implies E and M. This takes the form P implies Q, and therefore we can infer P implies P and Q, where our P is E and our Q is M. Again, clearly it is an example of an absorption. Okay, so that ends our lecture now. I hope you have a clear grasp of the rules of inference. So the next video would allow us to use the rules of inference in proving arguments. So I think we're ready for the formal proof in the next video. In the meantime, stay safe and stay healthy. Till next time, class.